Hello, hi, I'm Will, and I'm going to be giving a talk on modeling. How do I put this? Is this in presenting mode, or? Yeah, it is already, cool. I'm going to be giving a talk on modeling your dependencies as generative properties. Now, before I begin, I want to say that I work at Ecotricity. We're based in this building on the 5th floor, and we are hiring. We're hiring for mobile devs. We're rebuilding our app in native, which is one more than native. And we're also hiring for node devs. We're doing a lot of AWS Lambda stuff. It's very cool. So if you wanted to cut your teeth on some new technology, or if you're good at that stuff already, then talk to me or Henry. Henry's in the middle of the crowd there. Let's give you a little wave there. Yeah, cool. All right, can everyone hear me and see this? Yeah, all good? All right, cool. So yeah, I want to talk to you about property testing. It's a technique that I think a lot of people may not have, well, they may not have used, they may have heard of. It's to do with unit testing, so hopefully you all do unit testing. If you don't, just leave now, it's fine. I'll give you a minute. Yeah, and then after that, I'm going to introduce an idea that I'm not going to say I invented it. It's not necessarily a novel technique, but it's something that I found really useful when I was writing software for AWS Lambda, which is using JavaScript, and we've got a lot of first-party dependencies of Amazon services. Yeah, so before I begin, I decided, in case this is a terrible talk that's quite dry, I wrote some jokes. Yeah, I mean, some people are worried now. I can see it. So you do have to laugh, otherwise it'll be really awkward. Which JavaScript framework do farmers use? Mootles. Yeah, there you go. Setting the level now.
I think that crowd are too young. I thought you said jokes.
I'll try and press you. What is the Kaiser Chiefs' favorite programming language?
Ruby.
There we go, yeah. And then why do TypeScript programs take a long time to write? Because it's a gradually typed programming language. So I do have a few more, but I'm going to make you wait. There's going to be a few more halfway through, and then at the end I've got the rest of them. Then I'll be off quite quickly, I suppose. So how do I move on to the next slide? Press spacebar? Oh, God, that's too far. All right. A refresher on property testing. How many people here do unit testing or have heard of unit testing? Hands up. Okay, good. That's quite most people. That's excellent. That's good news so far. So property testing is pretty similar to unit testing. It's kind of similar techniques. Most people have used example-based testing. This is my analogy or my metaphor for example-based testing, okay? Got one little Nerf gun. It's pretty accurate. You can be very specific, but that's about it. You put in an input, get an output, compare them, good or bad, ship your software. This is property testing. Yeah. So property testing is a form of unit testing. It doesn't replace unit test, traditional example-based unit testing. It complements it. It's instead of working with specific inputs and outputs and saying, if I put in A, I get back B, yes or no. Instead, you talk about spaces of inputs. So you might say, can my program accept any integer or any string or an object that has these properties, but some of the properties are bounded in certain ways, or an array of those things. And then you then check, given those inputs and my app, do these properties hold? I'll give some examples. One of the clever things about property testing is that if one of those properties don't hold, here's a specific example. Let's say you've written your own sorting algorithm and it works on arrays, and it finds that an array of 100 numbers long doesn't sort in the way you expected. It will then automatically know how to shrink that down. So it will try an array of 99 numbers, then 98, then 97, and then it will, if the number at the very end is 5, it'll try 4, then it'll try 3, and it'll keep on trying to find the smallest possible failing case. You'll see that in a second. The other nice thing about property testing is it allows you to become a cyborg developer. Now, I'm not going to explain what that is. That's foreshadowing. But if you pay attention, you'll get it. Yeah, so it was invented by a man called John Hughes, who was pretty important when it came to, he's still alive, so I say was pretty, he's still pretty important when it comes to software development, very heavily involved in functional programming, was heavily involved in Haskell. And he says, as you can see, can everyone see that? Don't write tests, generate them. Okay, so he said people spend all their time writing all of these unit tests, hundreds of thousands of lines long, all these different unit tests, and they just clog up your code base. It means making changes is harder work. You can never be done writing unit tests because here's a classic example. People try and use code coverage to prove we've done enough testing. We've got 90% code coverage, we've got 95, we've got 100% code coverage. Every single line in my program is touched by a test in some way. Well, what if you're dividing a number by 0? Okay, what happens if that, let's say you're doing foo divided by bar. Have you tried making sure in your unit test that bar is 0? You'll still have all this code coverage saying everything's fine, but actually there's one more test that would have caused your program to explode. You ship it and everything is a big disaster. So you can never really be done writing unit tests. So he makes the point that, don't write unit tests, use property testing. He said this in a talk, it's a paper called Testing Experiences with Quick Check, Testing the Hard Stuff and Saying Sane. He also did a talk on property testing in general that's actually better than this one. So if you get the chance, do watch that. It's been ported to many different languages, so you don't have to use Haskell to do property testing, which is why I'm here at Bristol.js. There are lots of different JavaScript libraries to do property testing. There's maybe 3 or 4. They're all in various degrees of lack of maintenance. I'm going to be using FastCheck for my examples. It's one of the few modern, well-maintained property testing libraries for JavaScript. However, I would say that I'm biased because I am one of the top 4 most prolific contributors to FastCheck. Thank you, thanks. Yeah, fixing a typo in the documentation. Yeah. But that still counts. That still counts. And I'm number 4. I actually, in the process of putting this talk together, I found another typo in the documentation, but I didn't want to send a pull request in case I got bumped up to number 3 and that ruined the visual joke. So there you go. That's my level of dedication to my craft. So yeah, now that's enough spiel. I'm going to take you through some examples to show you what property testing actually looks like in the real world. I don't know whether this will display particularly nicely on this screen, so let's give it a go. Can people see that? Is that bright enough? Okay, cool. So if you can't see it, I'll explain it. It's like a classic unit test. You've got your testing function, whether you're using Ava or Mocha or Jest. Doesn't matter. FastCheck will work with those. There's either per testing library integration or you can do it manually. It's kind of up to you. It doesn't matter. You have your description of your test. It's, in this case, we're testing a function that checks if a string contains another string. Does A contain B? That's what we're testing. It's our own implementation. We want to make sure it works. I didn't write this test myself, by the way. I took this from the FastCheck documentation, so you can find it there. I'll take you through it. You've got the body of the test here. Does text, if you pass it to contains text, does it contain itself? We run it 5,000 times. I'll explain what that means in a second. The thing you probably don't recognize is this bit here. If you can't read that, it says fc.string. So fc stands for FastCheck. You'll see that a lot in all these code examples. But the important point is that it's calling a function called string. This gives you back a generator. Now, a generator is not in the sense of a JavaScript ES 2015 or 2016 generator. It's not a generator function. It's not a generator object. It's a specific idea for property testing. It's not a value at this point. It hasn't given you a string. You have to plug it into a function, like this one. So if you plug it into the test prop function, it will run the body of our test here 5,000 times, and each time text will be a different string. And it could be anything. So it could be foo, it could be bar, it could be an empty string, it could be some Unicode monstrosity, it could be Chinese, you never know, right? It will try as many things as possible. Looking at this, we think that, let's say this is foo. Well, foo should contain foo, right? That's how the contains function should work. So we think this property test should pass. That should be good. If text is bar, bar contains bar, so that should pass. Here's another property test. This is slightly more complicated. This is describing that a string should always contain its substrings. Okay, we're seeing a body here test body here where we get A, B, and C. These are 3 separate arguments, and we're checking that A plus B plus C should always contain B. Okay, so if you add 3 strings together, the middle string should be inside those 3 strings you added together. This is a little bit more complicated here. We've got an array of generators here, and actually they match up. So the first one here in the start of the array is A, the one in the middle is B, and the one at the end is C. They don't have to be strings, they could be whatever you want. They don't have to be an array of all strings, but in this case, that's what we want. Yeah, and it will run 1,000,000 times. That's actually not too slow, even for JavaScript. So let's have a look at our implementation of contains, and we'll see if it is going to pass our property tests. So this is our implementation. Hope I did a good job. What do you guys think? Not convinced? So this is taking the two arguments, and we're comparing them to each other. So text equals pattern. So if that's foo and foo, well, that should be true because foo equals foo. If it's foo and bar, then they won't match, so it'll fail. So this should work, right? This will pass first time. I'm pretty confident. Let's see what happens. It fails. Okay, so let's see which properties actually failed. The first one is actually should always contain itself. That actually passes because remember in that property we were passing the string 2 times into that function. So if we're comparing them equally, that will always pass. That's good. But comparing the substrings, that fails. And we're going to see exactly why. So fast check will show you the smallest failing case. As I explained with property testing, it will shrink. It knows how to shrink things down. So let's have a look at that. So it's pointing out that the smallest failing counterexample, that's the terminology it uses, is an empty string, and a string with a single space in it. Yeah? So let's consider this. If it was, let's say they're foo, bar, and baz, well, that's going to fail because foo, bar, and baz is not equal to bar, which would be the middle string, right? Whereas if they're 3 empty strings, well, an empty string, add an empty string, add an empty string is just an empty string. So it's not going to be this, it would be the same as the middle one, which would be an empty string, so that would pass. So fast check has shrunk it all the way down until it's found that if you add an empty string, and a string of a single space, which gives you a string of a single space, that does not match an empty string. So it fails. Okay, that makes sense. And let's see if we can fix our implementation to get it passing both properties. So I've gone with index of. Everyone's used index of. It's finding the index of a needle in a haystack. Okay, so it gives you the index of the first character in a given target string. So we're making sure that, let's say that's foo and that's bar. Well, foo and bar would give you -1 because it can't find it at all, whereas foo and oo would give you 1, right? And then foo and fo would give you 0, foo and foo would give you 0. So I think this is going to work. We're making sure that the index is always greater than 0. Let's see what happens. Oh, they both fail. Okay, there we go. So why do they both fail? Why would that be the case? Let's see. The reason why is that, let's start with the simplest case, which was passing the same string into contains twice. So foo, index of foo. What does that give you? 0. Perfect, yeah. But our test was checking that it's greater than 0. Very good. There you go. All right, let's see what happens. Well, actually, let's check the other property because that's what I put in the slide, but that's good. Jumping ahead very, very slightly. Oh, did I go forward? Yeah, there you go. So it's actually finding that 3 empty strings, if you add them all up, you get an empty string. Well, the empty string index of empty string is 0, so it's failing for exactly the same reason. Let's try and fix our implementation. Let's go with greater or equal to 0. Thank you. It passes. Amazing. There we go. Both our properties pass. You can see actually that should always contain itself took long enough that our unit testing library wanted to explain it. It took 242 milliseconds. So you can kind of see how property tests take a little bit longer than standard unit tests. I also wanted to show you that you can do more than just generate numbers or strings or very simple things. You can actually generate compound objects. You can generate arrays of things. You can generate recursive objects. You can generate almost anything you like. If you wanted, you can generate dates or custom classes if you've built your own class or if you're importing a library. As long as you can take the built-in generators that FastCheck provides you. We've only seen string. But as long as you can take those values and turn them into some custom data structure, then you can do whatever you like with it. Let's try and generate a shopping list. Can everyone see that? I know the contrast is a little bit low. So this is a shopping list. We want our shopping list to be an object with 3 properties. The first property is title, and it should be so-and-so shopping list. Or every time we generate a shopping list, we want that to be the title with whoever's name in the place of X. We want a date, because we want to know when we're going to go shopping. And if we find it later, we say, oh, 6 months ago, I was shopping for that. And then we also want an array of items, where each item has two properties. The actual item itself, which would be a string, that'd be bananas, apples, whatever you want, and then the amount, which would be the number of those things. So pretty straightforward. Let's see how we would put that together in FastCheck. This is going to look a little bit dense, and that's partly because I'm trying to fit it all in one slide. Normally you would use, you'd assign things to variables, give them names, put them in different files, you do whatever you need to. So don't freak out. Can everyone see that? That's way too small. Okay. All right, I'll take you through it. So at the very top, we've got constant from. Now, constant from is a FastCheck function that takes a series of arguments. In this case, I know people at the back can't see anything. This is a series of strings like apples, oranges, toilet paper, cereal, tofu, and hummus.
Is this the arbitrary monad from quick check?
Yes, it is. Yeah. Then we're producing a set of those products. Okay, so you can't see this, but this is FastCheck set. It will produce a unique array of any other arbitrary you give it. So in this case, we're saying create a unique set of products. So it will give us a random arrangement, which could be of any size, could be 5, could be 10, could be however long, of oranges, apples, toilet paper, cereal, the other things. We then see, this is going to be difficult to explain because you guys can't see it. Effectively, what we're doing is we're then using the chain function. Chain functions work exactly the same as promises do. Okay, so if anyone's used promises before, you have the then function. It's a method that you pass a function into, and that inner function will be invoked when the promise resolves. It works exactly the same for property tests, except they call it chain rather than then. It's almost the same. For the purposes of this talk, it will be the same. If you're interested in why it's not quite the same, I can bore you about it later. Effectively, what we do then is we take that item that we generated and we create a random amount. You guys can't see this. FastCheck integer from 1 to 100. So that means we get 100 toilet papers or toilet rolls, I suppose, or 50 or 10 or however much you want. At the very end, we chain it once again. You can keep chaining property tests generators for as long as you need to. And we then combine it. See, this is quite good, but you guys can't see it. We take a title, which is a constant from Will Heslam, John Hughes, and Philip Wadler, okay? And then we map it in the same way you map an array to check if it ends with S, you add a little apostrophe. If it doesn't end with S, you add apostrophe S. So you're handling the pluralization there. And then on the very end of that, you add shopping list. Okay, so it's going to produce either Will Heslam shopping list, John Hughes, or Philip Wadler's. This is an interesting bit. The date, we use fcnat, the nat arbitrary or generator. This will produce natural numbers. So that means 0 to effectively infinity, as opposed to the integer generator, which can give you negative numbers. We then map it into a new date. And it's that simple. Now you've got a generator that produces dates. It's that easy to turn something into a generator that produces primitive values into something that produces more complex ones. That's about it. Let's see what examples it comes up with when we run this through. There's a sampling function that you can pass any generator to, and it'll produce examples for you, so you don't have to test them straight away. Yeah, so there you go. You've got Philip Wadler's shopping list. On the 23rd of January 1970, about midday, just after midday, he went shopping for 92 toilet papers. He should have bought a whole roll, really. But he's got 46 hummus. And he went for just... well, exactly, yeah. You would need that. And 2 apples. Got to have some fibre in your diet. So that's what Philip Wadler went and bought on the 23rd of January 1970. John Hughes, and you can see there's a nice S apostrophe rather than S apostrophe S. About 5 milliseconds after the new... Sorry?
The beginning of time.
Yeah, the beginning of time. 5 milliseconds after the beginning of time. He was just seeing in New Year's Day, 1969, and he thought, just got to pop to the shops. And he got 4 apples, 18 oranges, a load of hummus, some cereal this time, and a bit of tofu. And then for good measure, let's see what my shopping list was. Oh. Oops. So yeah, on the 22nd of January, 1970, at about 20 past 1 a.m., I just panicked. I went to the supermarket and I panicked. Did they have supermarkets in the 70s? I don't think they did. Anyway. So yeah, I bought nothing. I panic bought. Yeah. Okay, there we go. Yeah, and this is an important lesson, which is that arbitraries can give you kind of really unexpected stuff. We were expecting a shopping list, and what we got was an empty thing. This is actually a strength, not a weakness, because if you've written your function and you're assuming that you're going to take all these values and change them, transform them, you're making assumptions about how long it is. You assume, well, why would someone call my API if they didn't have a thing to give me? Well, guess what? They might not be giving you anything. So yeah, now we're going to do a demo. We're going to see how property testing works with Oracle functions. Now, Oracle functions, they're not a special feature, they're just a way of using property testing. And the way it effectively works is, let's say you've got a pre-existing implementation, implementation A, and then you write your own implementation B because you want to make it faster, you're refactoring, for whatever reason. You can say, you can build a property test that says, for all of these inputs, do function A and function B agree with each other? That's it. You just say, does the equals function A, function B? If it doesn't, then fast check will find that failing case. It will shrink it down and it'll present to you and say, look, these implementations don't agree with each other for this small failing case. So it's pretty cool. We're going to be doing this with FizzBuzz. Does everyone here know FizzBuzz? Yeah? Okay, cool. All right. I need a volunteer. Does anyone want to volunteer? So effectively what's happening here is we're creating an integer from 1 to 99. And I'm going to make that a little bit bigger so you can see it. Yep. And then we're chaining it into a record, which is essentially an object where you have some fixed keys and then some values, which are also generators. And we're saying that the property start will always be whatever was passed in. So let's say this is generating number 50. Start will always be 50. And then we generate end, which is an integer from start to 100. So let's say start is 50, then end could be 75 or 199. So we're essentially generating ranges of numbers. We then, our test body is calling our oracle, our FizzBuzz oracle, and everything it prints, it logs to this array. And then we pass in our start and our end range. And then we've got our implementation, our solution, prints to the same array, start and end, or similar array, and then we compare them. Assert that the solution log and the oracle log are the same. That's it. It's that simple. It's going to run 10 times, although you won't see that. So, would you like to sit down? Take a seat. So, FizzBuzz.
I thought we were just going to play FizzBuzz manually.
Oh, we could play FizzBuzz manually. So,
Probably should have been listening more.
It'll be fine. It'll be fine. What could go wrong? So, FizzBuzz. How does FizzBuzz work?
So if it's a multiple of 3 or it's multiple of 5, then it's buzz, otherwise it's fizz?
Yeah, more or less. Yeah. Well, you start off by printing all of the numbers.
Okay.
And then if it is a multiple of 3, it's fizz. Multiple of 5, it's buzz. So let's start with that.
That's what I said, right?
Let's not go off script. Okay, cool. So let's start with a...
People think this is scripted. It's going to go really badly.
Should we start with a for loop?
Go on then.
So yeah, we got a start and an end.
That's where you're all going to find out that I'm actually a Rubyist.
It's fine. It's fine. So we will start at start. So it'll be fine. It'll be fine. It'll be fine. I wish I'd rehearsed this.
I should have let him write it with the wrong one, actually, because it would have been a really good...
That's a good point. That's a good point. So instead of using console log, we're going to use print. And we're going to print the number. You know what? Let's stop there. I think we're done. That works. Let's see what happens. Can everyone see that? Yep. npm run. Oh. FizzBuzz. Hopefully this will work. Can everyone see that? So it's going to take a few seconds because it's trying all the variations. So remember that it's testing Adam's implementation, his perfect implementation, versus the Oracle that we downloaded from Stack Overflow a few hours ago. Oh, okay, let's scroll up and see what happens. Okay, so it's found a problem with your implementation. Sorry, Adam, you haven't got the job. So the solution that you implemented goes 1, 2, 3, whereas the Oracle, hopefully everyone can see this, goes 1, 2, fizz. So we've made a mistake. So how? I know. So let's fix that. What's the best way to check?
I think we'll do some modular stuff.
Okay, cool. Let's go with that.
I think maybe we'll say if I over
modulo. Yeah.
3, then let's return some buzz.
In this, so yeah, you'll have to print. Sadly,
Of course.
it's side effecting. I don't like functional programming anyway. It's a waste of time.
That's where you find out. Are we not implementing this?
Let's go with buzz as well. That's fine.
Yeah.
Why not go all the way?
And are we doing fizzes or are we giving ones and
We'll do that afterwards. It's fine. We'll go. That should just be. That should just be the number, right?
I don't know. I forgot how fizz.
That's fine. That's fine. Let's go with that. Let's run it. Okay. Let's not panic. It's fine.
I feel like I'm being interviewed in front of a room of 100 people.
I feel bad. I feel bad.
Like,
Okay.
what only a small % of you know is despite running the JavaScript group, I actually quite dislike JavaScript.
Yikes.
I just think it's really important. So where are we?
That didn't quite work. So that's fine. But so what we can do is we can actually check that the modulo of 3 is equal to 0, which is what you need to do.
That would make sense.
That would make sense. And then we're going to also change that to be fizz, right?
Probably.
Fizz. And then we're going to go with same thing here, same treatment, equals 0. Cool, let's see what happens.
That's why you should always pair program, kids.
Or use an Oracle function.
Or
Takes all the hard work out of it. Okay. Okay, so it looks like our solution goes 1, 2, fizz, good. 3, whereas our Oracle says 1, 2, fizz. It doesn't print the 3. The reason why is we've forgotten else. So yeah, I'll just put the else in there for you. Oh God, now I've forgotten how else's work. It's all fine, it's fine. Yeah, is that good? That'll work.
Nobody's watching, it's fine.
Yeah.
You also need to capitalise the ad.
Okay.
The Oracle's using capital ad.
You're absolutely right. There you go. Okay. So it found, this time it didn't go with 1 because it's found the more interesting failing case of 2, fizz, 3. So let's capitalize that. Buzz. Okay, let's run it, see what happens. You're doing a great job, Adam.
I feel like it. It's what I do, I delegate.
And then we'll see what the error is. We're not meant to be printing the number, so let's get rid of that as well. That should be inside an else here. Cool, good. It's always a good idea to be doing live debugging. Okay, this is more interesting. Look what happened. Well, look at what's happening here. So the solution goes, and actually that's kind of hard to read, but I think that's the solution here is 1, 2, fizz, 4, buzz, fizz, 7, 8, fizz, buzz, 11, fizz, 13, 14, fizz, whereas the Oracle goes up that way, and then it says 13, 14, fizz, buzz.
Wow.
So we've got to handle the final one. Do you want to try that?
Why not? Probably a more efficient way of doing this.
Oh, this is
We
fine.
could shout out that we could do like world's largest session of like pair programming, but for now,
it's going to be a...
somebody's already solved it. We could have done this if we just went to Stack Overflow. So, you know.
for the sake of efficacy,
Oh,
we
wait,
want
yeah.
ampersand, yeah.
Module actually just downloads the pop-up voted answer of Stack Overflow and runs it.
There's got to be a VS Code plugin now, which is just tell me what to do.
A moment of truth.
Oh, what did we do wrong? What did we do wrong, Will?
What did we do wrong?
Oh, syntax error. Oh, dear.
Where is that syntax error? Else if.
Well.
There we go. Property testing, everyone.
Fuller of regret.
No, it's fine. You're doing a good job. I mean, if it, yeah, okay. Yay. Thank you, Adam. You've done a fantastic job. You've got the job. When can you start? Okay, so that was the FizzBuzz demo. So now you see how Oracle functions work. You can use this if anytime you're refactoring or you're implementing something in a more efficient way, or you just want to mess around and see what happens. You can compare two different functions. One of the interesting things about generators is there is an art to writing a good generator. Here's a specific example. Let's say you want to generate even numbers. Let's say you want to generate 1,000 even numbers. How could you go about this? These generators will both do that for you, okay? But I want to explain the differences. So this one here, if everyone can see that, you're generating a natural number, and then you're filtering it just like an array filter, and you're making sure that each number, modulo 2, is equal to 0. So that's a good classic way of testing if something is an even number. What this will do is it will generate 2,000 numbers, even and odd, and throw half of them away and give you 1,000 even numbers. So it's essentially 50% inefficient. It's doing twice as much work as it needs to. Whereas this implementation here takes natural numbers exactly the same way, but instead it maps them and multiplies them by 2. Okay? So if that's 1 multiplied by 2, 2. 2, 4, 3, 6. The point is, if you need 1,000 even numbers, this will generate you 1,000 even numbers just like that. The key thing here is that as I've said here, the description is not the recipe. Often it's the best way to generate a valid value that you want to use in your tests is using a recipe rather than filtering based on a description. It's a bit like on a factory line, okay? Let's say you need to produce something like the iPhone. You can either try completely random collections of metal and bits of glass and then check, is this an iPhone? No. Is this an iPhone? You'd be there all day. It would take you ages, right? Whereas if you have an instruction manual that explains how to combine glass and metal in a particular way to make an iPhone, you'll make one almost every time. You might want to filter out the defective ones at the end, but now that gives you a good intuition for how to build good generators versus bad generators. It's bad to have a bad generator. So, yeah, next slide. The other thing I want to talk about is the fact that a lot of unit testing libraries will encourage you to use before and after blocks to do test setup and tear down. That's not going to work with FastCheck, and it probably won't work with a lot of the property testing libraries you use because they typically run their properties, they exhaust all the combinations inside a given test. So your before and after will run once, and then it will run 1,000 actual tests. So if you're doing any side effects, if you need to reset the state of something, it's not going to work how you expect. You won't just be able to dump it in. FastCheck gives you some facility here. It gives you these before and after functions where you can essentially copy-paste your setup and tear down stuff put in there. However, I would suggest that actually tear down and setup functionality is essentially mutating global state. That's why spies and mocks are a workaround. They're a spider to catch a fly. And actually, you're better off not doing that at all. If you can instead pass in your values into your functions, your dependencies into your functions using dependency injection, it may mean your code is a little bit more verbose, but in the long run, you're trading ease for simplicity, and that's usually a good trade-off. That's why I have this catchphrase. Don't side effect, dependency inject. I'm always saying it. That's a common catchphrase you'll often hear me say. a lot of you will be thinking, well, my code can't be tested. I write untestable code. It's a badge of honor. Well, actually, anyone who's done unit testing for a little while will find out that, first of all, it's hard to write tests until you change the way you write code to make it to make it testable. And actually, the same is true for property tests. People will be sitting there thinking, I'm just imagining what you're thinking, I can't think what properties would apply to my code. This all seems very complicated. My code just does one thing and another thing, then it's done. It's nice and simple. Well, actually, you'd be surprised. If you take a little while, look at your code, think, could I pull this out? Does this have a property that I could test against it? It doesn't even have to be particularly complicated, okay? So it could be that for all of these inputs, my code never throws an exception. That's a perfectly valid property to test for. And that's a good property to test for. If you want your code to be robust, you want exceptions to be thrown in specific circumstances. You don't want it to just explode randomly. Yeah, it doesn't just provide robustness. It also allows you to think carefully about the way your code works. It allows you to think, well, I may be using this for user IDs, but actually it'll work for any string. If it's sorting customers in a specific order, for example, you might think, well, actually I can reuse this elsewhere in other places because this works generically for all strings rather, or all numbers instead of specific concepts. Yeah, and that's actually the end of the first part. Don't worry, the second part's not as long as the first part. But that's introducing property testing. I'm now going to be explaining the specific technique that I used at Ecotricity to test my Amazon serverless functions and the way you rely on dependencies like DynamoDB or Kinesis or various technologies that Amazon gives you. I developed a technique of using property testing to simulate those. But I'm going to tell some jokes again. Yeah. Why do functional programmers never get lost? They always use maps. Oh. If you didn't like this one, you're going to hate this one. Why did it take 20 years for JavaScript to get classes? They spent too long prototyping. All right. So, modeling dependencies as generative properties. Are dependencies any different to function arguments? In my opinion, I would say no, they are the same thing. I think it's a false dichotomy that people think of values and then the rest of their program as fundamentally separate things. I think you can actually treat your dependencies as value spaces in much the same way you treat any other kind of input to your functions. The reason why I started thinking this way is I was working with a lot of documentation that was lacking. It wouldn't be obvious what, for example, a database might return in a given context. If you're working with an eventually consistent database that might return one value at one point and another value at another point for the same operation, well, at this point you need to start using these kind of probabilistic techniques to simulate that. Yeah, instead of guessing, why not try everything? This leads me into Postel's law. Can you see this? He said that you should be conservative in what you send and liberal in what you accept. It's less a law and more an economic principle, really, that if you're dealing with any distributed system, whether it's network requests or whether it's things in a file system or a database that changes over time, you need to be able to cope with change that you can't predict. There's no type system that works across the network as much as people would like to believe there is. So this is the only rational way to deal with change. Now we're going to look at another demo. This is going to show off, don't worry, I don't need a volunteer, so relax. This is going to be showing off modeling your dependencies as generative properties. So what we're going to be simulating here is a pizza delivery service. Okay? This is an API call that accepts as its dependencies, it's a dependency injection, a database, and a city map. And then it responds to a user's request of their order and their address. So their order would be a pepperoni pizza, and their address would be wherever they live. It then adds that order to the database. So this is a dependency here, you're adding your order, and the database will return back a cooking time, how long it will take for that pizza to be ready. You then take the address and the cooking time and pass it into the city map, which will give you an estimate, a delivery estimate, and you return that to the user. So if you want to order pizza, it'll tell you, oh, well, it's going to take 20 minutes to cook. You live on the other side of Bristol, so it's going to take 40 minutes to get there. This seems pretty straightforward, but actually there's plenty of ways this can break. Ahead of time, I put together a fairly complicated looking property test that simulates our dependencies. Hopefully you'll be able to see this. I'm going to show you a kind of keyhole view of what's happening here. So we're going to simulate our database by creating an array of either an integer, undefined, or a string of database error. Okay? And our city map is going to be simulated as bear in mind the integer would be how long it's going to take for the pizza to cook. And then the city map will be how long it will take to get across the town. It could return undefined because the API has gone down, or it could return an estimation error. What we do then is we store the number of times the database in the city has been, the city map estimation has been invoked. And we expose these as functions. So every time an order is added, that's exactly the same add order function you saw before. If there is no order, it throws an error. Otherwise, it increments a database count, modulos it with the length of the pattern that we just generated before, which was going to be an array of numbers or undefined or a string. If it turns out it's a database error, throw an exception, else return the value. Okay, so let me explain what that would look like. Every time you generate, let's say it's an array of 10, 15, database error, undefined. First time the database add order function is called, it's going to return 15. Second time it's going to be 15. Third time it's going to be database error, and the fourth time it's just going to return undefined. We do exactly the same thing for the city map. I'm not going to go into details here, but it's exactly the same principle. We then generate our orders. So you can see here, pepperoni pizza, margarita, veggie pizza. We're going to have one of each. We're going to generate a quantity, and this is our array of our orders. And our address is just an array of strings that we combine. That's fine. This is our test. The way it works is we invoke our API. This is exactly the same function you saw before. Okay? And then we iterate through the results, and we make sure that for every invocation, we either got back a status of success and a delivery time that's a delivery estimate that's a number and greater than 0, or a failure message, or an error with a message that the user is happy to see. We're not exposing any internal implementation details. That's it. That's the entire test. So let's see what happens. Oh, okay. And we're going to be running this. All sorts of errors. We have to have at least one order. We have to, because it could generate an empty array. There's all sorts of exceptions that could be thrown. Luckily, I fixed this beforehand, so we're just going to use that instead. So I'm going to show you what that looks like now. Here we go, pizza fixed. Can everyone see this? So first of all, we check that the order length is 0. If it is, we return fail, need at least one order. We check the address, at least one order. Address should have at least one value, okay, there's a typo. We get the cooking time. If it turns out it's not a number or if it's less than 0, we return a complaint. We get back the estimated time. If it's not a number or if it's less than 0, we give you a guesstimate, because at least the order's gone in. We know it's going to take half an hour to make the pizza. We don't know how long it's going to take to get there, but we can tell the user it's going to take an hour. That's fine. So we've got a fallback there of 1,000 times 60 times 60. And then we return success. So this is an example of how if you have a dependency that could return all sorts of broken values, such as undefined or throw an exception, we're handling it. In the very end, we try and catch and wrap the entire thing so we don't expose any internal implementation details back to the user. So let's run that again and see what happens. Hopefully it should pass. There we go, that's good. So it passes, and furthermore, I logged out all the examples of database and city map patterns that can be produced. So you can see here that it went through all the iterations. You can see that you've got the first time the database was called database error, second time undefined, negative number, city map undefined first time. So it's that easy to simulate your dependencies using properties. Are there any downsides to this? Yeah, there are some downsides. So the downsides are that there's a disconnect between your app code and your generators. Okay, so your generators can be trying all these different combinations. Here's an example. Our database produced a database error. That was all it's going to ever produce. But our city map would have produced all these interesting values. But we know from our logic that if you didn't get an estimate on the cookie time, you would never try and even get an estimate on the delivery time. So this is wasted exploration of this phase space of your dependencies. Same with this one here, database is undefined, so we know the order wouldn't go through, but we're testing all these different combinations of undefined, large positive number, large negative numbers. This is wasted computational power. Nothing of value is being tested here. Is there a solution? So there is a solution. What if you could design your app code so that it constrains the dimensions of your dependencies? What if you could make it so that if you're not invoking the database call 5 times, it will never try and explore these different combinations? There is a way to solve this. I actually solved it in the run-up to this talk, which is quite good, using a custom monad. Now, you don't have to know what monads are, but effectively it wraps the property generator with a way of storing state and a way of doing error handling in the same way that promises work. By reframing your program as a sequence of monadic steps, you can constrain the dimensions of your dependencies to your business logic. Let's see what this would look like. Here's a contrived example. So the contrived example is this one right here. So we're generating A, B, and C. Oh, sorry. Yep. Can you see that? Yeah, you can see that. Cool. Okay. So we've got a simple property test here where this is foo, this is simulating, say, our database. Bar might be simulating the city map from before. It can be whatever. It's just arbitrary different dependencies. Foo, every time it's invoked, returns a value from A, B, or C wrapped in this custom monad. It then stores what value was generated in this state here. You don't have to know too much about how the state handling stuff works. Just assume it does for now. Bar does the same thing, but for 1, 2, and 3. It just stores it in place. So it's very, very simple code. A, B, and C, store it. 1, 2, and 3, store it. And then we have a very simple property test here. It's actually just logging out what the state would be. It doesn't do any actual testing. We then invoke our function here. This is our app code called enumerate. Now, enumerate takes our dependencies and it only uses foo. So it invokes foo, and then with the result of foo, which returns a monad that has a chain function, remember that's exactly the same as the promise.then. So imagine this is then. We then invoke foo again. And then we chain and invoke foo once more. So let's see what that would look like. We don't want to be seeing any numbers, just letters. Perfect. So you can see that it's trying all the different combinations of CBC, ACB. You can see it's trying all these different combinations. You'll notice here that, unlike our example before, there's no different numbers. It's just letters. That means that it isn't trying to explore that space of the dependency it never uses. It understands you're only ever using foo. To show how powerful this is, here's a more complicated example. This is the same version of the business logic, but the first time we call foo, we check if x is equal to b, then we invoke bar twice, or just foo. So let's see what that would look like. Cool, so you can see that when B was the first result, it actually did this, it used another dependency in a different way, and that phase space was explored. It did try 2 and 3. Whereas for all the examples where it was C or A, it didn't even try exploring that space. So it's essentially wrapping all those combinations that it was trying blindly before. It now understands that you're using only a specific part of your dependencies in your test. And the reason why is that the app code is now generating the properties itself. It's no longer in the test body, but your app code is creating the generators through this chaining mechanism. And that's basically, that's it. Yeah, I have a conclusion, and the conclusion is that, why have I told you all this? I wanted to, first of all, prove that property testing can make your code more robust. It can bust all of the assumptions that you make about what your function actually does. Instead of having to enumerate all these different example-based unit tests, it will just try everything for you and find the cases where you were wrong. And the other thing I wanted to show is that property testing doesn't have to just be used for simple values. You can actually use it to simulate processes or stateful systems. And there is some downsides with that. It can be quite inefficient unless you use this chaining mechanism. I will open source my custom monad at some point when I get around to it. Cool, that's it.